Swayam Prabha. Digital India. Educated India.
Welcome back. So, today we will be taking few more problems on stress distribution in soil. So, in the last lecture we have solved couple of problems regarding stress distribution in soil. So, today we will be taking few more problems. So, first problem is, the problem says that for a vertical concentrated load prove that maximum vertical stress on a vertical line at a constant radial distance r from the axis of a vertical load is induced at the point of intersection of the vertical line with a radial line at beta equal to 39 degree 15 minute from the point of application of concentrated load. What will be the value of shear stress at the point. So, this shear stress we have not given the expression when we discussed about the theory. However, we will be giving that expression here itself and we will be solving that problem. Okay. So, that is also I mean you can find out the normal stress as well as the shear stress at a particular point due to the application of the concentrated load. Anyway, so hence find the maximum vertical stress on a line situated at r equal to 2 meter from the axis of a concentrated load of value 20 kilonewton. Okay. So, let me draw it. Vertical stress distribution. This is Q, this is radial distance R, this is Z, this angle is beta equal to 39 degree 15 minute. Okay. So, this is the problem. The problem says for a vertical concentrated load such as Q, prove that maximum vertical stress on a vertical line at a constant radial distance r. Okay. So, this is the vertical stress distribution. If you solve this thing by Bouzinet's theory, whatever we have seen, okay, for a concentrated load, then you will be getting the stress distribution at any radial distance r from the concentrated load axis. You will be getting the stress distribution like that. So, it will not be maximum at the top, it will not be maximum at the bottom, it will be maximum somewhere else or at some depth z. Okay. So, from the axis of a vertical load is induced at the point of intersection of the vertical line with a radial line at beta is equal to 39 degree 15 minutes. So, you have to prove that this beta angle is 39 degree 15 minute. That means, the point where the maximum vertical stress is coming. So, that point, if you connect that point with the point where the concentrated load is acting. So, this line will be making an angle 13 beta, okay, which is equal to 39 degree 15 minute with the vertical axis. Okay. And what will be the value of shear stress at the point? So, you have to calculate the value of shear stress at that point where it is becoming maximum. That means, where the normal stress, that is the vertical stress is becoming maximum at that time, you have to find out the shear stress. We will be seeing the expression for that, and hence find the maximum vertical stress on a line situated at r is equal to 2 meter from the axis of a concentrated load of value 20 kilonewton. Okay. So, let us solve that. So, the vertical stress magnitude or the expression is already given in the lecture class. Okay. However, shear stress distribution we have not discussed, which will be discussed now itself, because we are taking this problem. So, we know, so solution, we have sigma z is equal to 3q by 2 pi z square into 1 by 1 plus r by z square to the power 5 by 2. This is known to you, right? Already we have seen this thing in the lecture class, isn't it? So, this is already known to you. Now, for the maximum value of of sigma z where r is constant. That means if you consider this vertical section, your r is constant, all the times r is same, right. So, r is constant. So, how I will get the maximum value of sigma z? So, this is the expression of sigma z. So, this sigma z will be differentiated with respect to z. If we do that, then we will be getting the maximum value of sigma z, right. So, differentiate the above equation with respect to z and equate it to 0. So, therefore, I have the expression like this 3 q by 2 pi. I am taking z in this term. So, the same expression z cube by r square plus z square to the power 5 by 2. Okay. So, this is the expression of sigma z. Now, what we will do? We will do the differentiation del d sigma z dz equal to 3 q by 2 pi, it will be 3 z square into r square plus z square to the power 5 by 2 minus z cube into 5 by 2 r square plus z square 3 by 2 into 2z divided by r square plus z square to the power 5. Okay. So, this is equal to 0. To get the maximum value of sigma z, this should be equal to 0. So, if that should be equal to 0, then what we will get? 3 z square into r square plus z square minus 5 z to the power 4 is equal to 0. Okay. So, which gives me z equal to root over 3 by 2 r, which is nothing but 1.225 r. Okay. So, therefore, r by z is equal to root over 2 by 3 is equal to 1 by 1.225 is equal to 0.817. Now, if you look back the figure, okay, so whatever figure we have given during the problem definition, at the time what is r by z? That is nothing but tan beta. So, from this I can prove beta is equal to 39 degree 15 minutes. It is proved, hence proved. Okay. Now, what are the things you need to find out? You need to find out the maximum normal stress and shear stress at that point. Okay. So, now substituting the value of r by z is equal to root over 2 by 3 and z is equal to root over 3 by 2 r. If I put this thing in sigma z expression, then I will be getting the maximum sigma z, right, in that expression. that is equal to 3q by 2 pi into 1 by 3 by 2 r whole square into 1 plus 2 by 3 into 5 by 2. So, that is giving me sigma z max is equal to 0.088 q by r square. Okay. So, that is your sigma z max, and the expression for tau r z is equal to 3q by 2 pi. Please make a note of this expression into r z square. Again, from theory of elasticity I can find out this r square plus z square whole to the power 5 by 2. So, which is nothing but 3q by 2 pi into r by z square into 1 by 1 plus r by z square to the power 5. Okay. So, now from this expression, if you compare this expression with sigma z max, okay. So, basically 3q by 2 pi that is there, and 1 plus r by z whole square, all those things are there. So, I can write this thing, if you compare those tau r z is equal to sigma z max into r by z. So, that is nothing but 0.0888 q by r square into r by z is what value? R by z already root over 2 by 3, that is nothing but 0.817. So, from this I can write 0.0725 q by r square. So, this is your tau r z at that point. Okay. So, as given in the problem, for r equal to 2 meter and q equal to 20 kilonewton, sigma z max will be 0.0888 into 20 by 2 square equal to 0.444 kilonewton per meter square, and tau r z equal to 0.0725 into 20 by 2 square, that is equal to 0.362 kilonewton. Okay. So, we have got the maximum sigma z at that location and also shear stress. I hope that you have understood the problem. Only new thing is that the expression of tau r z, that is the new thing we are introducing, and that is coming from theory of elasticity. As we have got the expression for sigma z, similarly we can find out tau r z also. Okay. So, now we will go to the next problem. Next problem says, what is the vertical stress? QV at point A of figure given below for the two surface loads Q1 and Q2. Okay. So, now it looks like this. This is the surface, here Q2 is acting, which is equal to 1000 kilonewton, and we are considering one vertical section below which you have the point A. Okay. At that location you have to find out the vertical stress, and you have another force, surface force, say Q1, which is equal to 500 kilonewton. The distance between Q2 and this vertical axis is R2 is equal to 1 meter, and this R1 is equal to 2 meter, and Z is equal to 2 meter. That means point A is 2 meter below the surface on which Q1 and Q2 are acting. Okay. So, this is the problem. So, we will be considering the point A, and we will be finding out the vertical stress developed for the application of Q1 separately and for Q2 separately, and then we will combine them together to get the resultant vertical stress, right. This is the way we will solve this problem. Okay. So, solution QV is equal to sum of stresses from the two loads. Okay. Now, for Q1, R1 by Z is equal to 2 by 2 is equal to 1. Just look at the figure, R1 by Z, that ratio of radius to depth, that is R1 by Z is equal to 2 by 2 is equal to 1, and for Q2, R2 by Z is equal to 1 by 2, that is 0.5. Okay. Therefore, QV is equal to Q1 by Z square into 3 by 2 pi into 1 by 1 plus R1 by Z whole square to the power 5 by 2 plus Q2 by Z square into 3 by 2 pi into 1 plus R2 by Z whole square to the power 5 by 2. Now, if we put the values of R1 by Z and R2 by Z, that ratio, as well as Q1 and Q2 as well as Z, if we put all the values, we will be getting this is equal to 78.8 kPa. Okay. I hope you have understood. So, if you have this kind of situation, that means when you have several concentrated load, and if you want to find out the vertical stress at certain point, okay, so you have to take the contribution of each individual load at that point, and then you add them together to get the total vertical stress increment or the total stress developed at that point due to the application of the concentrated load. Okay. Now, we will go to the next problem. Next problem says an L shaped area as shown on ground surface exerts uniform pressure of 100 kilonewton per meter square on the soil. Determine the vertical stress induced at a depth of 5 meter from the ground surface. Below point P as shown in the figure. So, this is the L shaped area, this is 10 meter, this is also 10 meter, this side is 15 meter, this is 30 meter, and this is the point P. Okay, you need to. So, an L shaped area as shown in the figure on ground surface exerts uniform pressure of 100 kilonewton per meter square, that is nothing but Q naught on the soil. Determine the vertical stress induced at a depth of 5 meter. So, Z equal to 5 meter from the ground surface below point P. So, now if you solve this, so basically this area you have to discretize. So, this, so P point is not coming as the corner of any rectangular area, right. So, as we have concluded or we have decided that any point, at any point you can find out the stress provided that point belong to some corner of the rectangular area. So, P does not come as a corner of some rectangular area. So, we have to make the area, or we have to discretize the area in such a way that P should come as the corner of the rectangular area. So, let us discretize that area. So, this is the original area, this is the point P. So, we are making 3 different area, this is A1, this is A2 and this is A3. So, this is your 10 meter, this is 15 meter, this is also 10 meter, this is 20 meter. Now, we are going to find, so at P, at 5 meter depth, QV is equal to QV due to total area is equal to QV due to area A1 plus QV due to area A2 plus QV due to area A3. Agreed? So, now P point is the corner of area A1, corner of area A2 and corner of area A3. So, now if we try to find out the vertical stress at point P due to area A1, due to area A2 and due to area A3, then if we add them together we will be getting the total stress, that is the vertical stress QV for the whole loaded area. Okay? So, that is the idea. So, for area A1, your M is B by Z. What is the shortest dimension for area A1? Area A1 is nothing but the square area. So, it does not matter, 10 by 5 is equal to 2, N is L by Z is equal to 10 by 5 is equal to 2. So, for M equal to 2 and N equal to 2, your I sigma 1 is equal to 0.232, that you will get from the table. Now, for area A2, that is your rectangular area. So, M is 15 by 5, that is 3, and N is 20 by, area A2 is something different, sorry, area A2 is 10 by 5, sorry, 10 by 5. So, that is your 2, and N is 15 by 5. So, 15 by 5, that is 3. So, M equal to 2 and N equal to 3. So, with for that combination your I sigma 2 is equal to 0.238, that you will get from the table. Similarly, for area A3, your M is 15 by 5, that is 3, and N is 20 by 5, that is 4. So, for M equal to 3 and N equal to 4, you will be getting I sigma 3 is equal to 0.245. Therefore, hence your QV is equal to Q naught into I sigma 1 plus I sigma 2 plus I sigma 3. What is the value of Q naught? That is given in the problem 100, 0.232 plus 0.238 plus 0.245. So, total is coming 71.53 kilonewton per meter square. Okay? So, this is the problem. So, this is the answer for that problem. So, at point P, at some depth say 5 meter below point P, you will be getting vertical stress as 71.53 kilonewton per meter square due to the application of uniformly distributed load Q naught, that is 100 kilonewton per meter square on the L shaped area. Okay. So, with that I will conclude this course. So, I hope that you have enjoyed this course and you have learned this course. The most important thing is learning the course, okay, because you may or may not get the opportunity to learn this kind of say very basic and fundamental course. I hope that you have enjoyed each and everything, every chapter, and feel free to contact me if you have any kind of doubt, okay, through the forum. Thank you very much and all the best for the exams. Thank you.